So this is the Muddiest Points mini lecture on organization and memory. In this video I'm going to talk about organization versus architecture versus realization, and I'm also going to talk about memory and addresses. I got a bunch of questions about add versus add-I and add-U and asking for more code examples. I've split the topics for this week up into two other videos. So this, if you click on this box over here, that'll take you to a video explaining these topics and looking at code examples. And if you click on this box over here, it'll take you to a video talking about the assembly language syntax and writing programs. Now in architecture, organization, and realization, what we're talking about is different levels of design in the processor. The first level is the architecture, where we're talking about the instructions that are available to the programmer or to the compiler. In the MIPS architecture, the add, sub, and load word instructions look like this, where they have a keyword add, destination, and two sources. The load word has a destination and a pointer with an offset, right? In the x86 architecture, it has a different syntax for the same operation. So add only takes two operands, sub only takes two operands, and instead of a load word, we have a move operation that still only takes two operands. So because of this, if I wanted to add two numbers together and put them in a third location, I would have to use two add instructions instead of just one add instruction in the MIPS architecture. So that means that the x86 architecture actually would require more instructions to do the exact same operation. Now at the organization level, the add instruction can be implemented in different ways. This is what we mean by organization. For example, the add instruction could use a ripple carry adder, which is slow but cheap, it's very simple, or it could use a carry look ahead adder, which is fast but expensive because it's very complicated. Now this is the organization level, which means that depending on what implementation I use, the add instruction will have an average execution time that's different. This would have a faster or lower CPI, and this would have a higher CPI. Now inside of each of these, the realization means how we implement the fundamental logic gates. So here we've got these AND gates that we need to implement, and inside of an AND gate is actually an electrical circuit that uses transistors and resistors and all kinds of stuff. How we implement these transistors is the realization part. So we could use a silicon transistor like we do normally, which is fancy and fast, and the smaller it is, the faster it goes. Or we could use a vacuum tube, which is much slower, but you know, at the time that we were using them, it was the hottest technology available, right? So that's the difference between architecture, organization, and realization. The implications for this is that the architecture determines the instruction count of a program. Depending on what instructions are available and how the instructions are formatted, the same C++ program might take more instructions on one architecture than on another architecture. The organization determines the CPI of instructions. The same add instruction might use slower hardware on one organization versus faster hardware on another organization. And the realization determines the clock frequency. Basically, the take-home here is that a smaller transistor or a higher technology transistor will turn on or off faster, which allows us to change the clock frequency. And that all goes into the execution time equation and determines how long a program will run on different architectures with different organizations and different realizations. Now let's talk about memory. Now I had some confusion, I think there's some confusion about what memory is and what the difference between memory and addresses are and all kinds of things like that. So let's take a little analogy here. Think of memory as a series of mailboxes, right? These are things that we can store information inside of, and each mailbox has an address. So the first mailbox has an address of 000, then 001, all the way down the street, right? So this is like your street address. It's a number on the street. In this case, there's only one street in the world, and that's our memory space, right? Now, each of these mailboxes can store some values. You can store a letter or a number or something like that. That's the data contained within the address, right? Data contained at the address. Now, our mailman has a knowledge of where everybody lives, right? So instead of referring to each of these addresses as by their number, we refer to them by a name. So you can think of it as whoever lives at that address. Jones lives at address 0, Smith lives at address 1, so on and so forth. So when it gets a letter, that says, I want to put the value 127 at Smith, what happens is he translates the name Smith into the street address, and then he can, once he has that street address, he can transfer that data into the street address location, and we've stored some information there. So the address 1 contains the data 127. Similarly, if somebody asks for what Smith has, he looks up the address, finds that information, and he can copy that back out, and we get the information back in. So that's how we store information. That first step was storing information at an address, and the second one was loading information from an address, right? Now, looking at registers versus data memory, both of these are types of memory in that they store values, but we most of the time refer to data memory as memory because it's the big data memory. We're going to use it a lot. We just call it the memory. The registers are distinct because they're small and fast. They're tiny little bits of registers. There's not very many of them, and they go really, really quickly. Data memory, or just normal memory, is large and slow, and that's how the big distinction between them is. Structurally, there's no big difference in terms of their technology. It's just whether one is fast and small or the other is large and slow, right? When we store information in a memory, it has an address, just like we were talking about. The address is the number of a location that stores some data, and we store everything as a byte. So every location in memory only stores 1 byte, right? 1 byte is equal to 8 bits, so we've got 8 bits lined up in every memory location. Now the problem is that 1 byte can only count up to 255. That doesn't leave a lot of flexibility for us. We want to count much bigger numbers. So what we do is we build a system using a 32-bit word, or 4 bytes at a time. This allows us to count up to 4.25 billion almost. But what this implies is that we have to treat, because we can't change the structure of the memory, we don't want to change the structure of the memory because sometimes it's useful to treat a byte as a byte. We have to count, because every word contains 4 bytes, we now look at memory like this, where each word consists of 4 bytes. So the first word starts at address 0 through address 3. The second word, so word number 0 starts at address 0 through address 3. Word number 1 starts at address 4 through address 7. Word number 2 starts at address 8 through address 12. Through address 11, and so on and so forth, right? So memory is still addressed as a byte. Now we have some memory and address instructions, and basically these are instructions that operate on memory and addresses themselves. The load address instruction translates that name that we had before into a memory address. So it figures out, based on what name or variable name that we give it, what the location in memory is, which is the address. And then it copies that address into a register. The load word instruction copies data from an address, so it gives it an address, it finds the data in that location and copies it into a register. The store word does the opposite, where it takes data from a register, finds an address, and copies that data into a location. So go to the next video and we'll look at some more examples of how to implement these concepts in assembly language syntax and writing some programs.